Now, let me continue with, again, these mechanisms. Now, how do we approach such problems? So I'm going to talk about basic steps of contracting problems in general. Okay, so the first one is you develop a supply chain model. Now, this supply chain model, of course, is going to represent each part. So you're going to have a decentralized part, and then you're going to have a centralized part. Now, the second one is, well, within this, you also obtain the centralized solution. So this is basically what is done in Pasternak, if you recall. This is model 1 and model 2. So you develop models to represent the decentralized and the centralized supply chain. Now, it usually turns out that to have the centralized solution is much easier. Because when you have everybody in a single structure, then there is less of a problem with respect to which decisions to give. Whereas if you have supply chain actors being connected, then you have to make sure that you have models which is going to give decisions for both sides. So the number of decisions will increase, of course. Okay. The second one is build a competition scenario. Now, this competition scenario actually is sometimes feasible, sometimes not very easy. Remember in the paper by Gerchak and Wang, you have an implicit competition between suppliers to the assembler. Okay? And we actually built up this competition scenario. We said that they have information from each other. Okay? And then they were able to show that a Nash equilibrium exists. So which means that they are only going to supply the same amount. Now, then what you achieve is some kind of an equilibrium. We call this the competitive solution. Now, it turns out that even if you don't have competition, you have vertical relationship between firms, you again have the notion of equilibrium. This is the model which was built actually by Pasternak. If you go one step further for Pasternak and optimize the problem for the manufacturer, okay, then you are again going to have some kind of an equilibrium. But it's not necessarily a competitive equilibrium, but it is a leader-follower type of equilibrium. Okay, so you obtain an equilibrium. And then the third thing is you compare solutions. In other words, you compare the decentralized solution, equilibrium solution, with the centralized one. Okay? And the fourth step is, after you do all of those, note that it's not easy to pursue on some kind of a contracting research, because basically, once you do this, you have to make sure that this competition scenario that you built is reasonable, of course. You cannot arbitrarily build a competition scenario. It should be general enough. Only in the fourth step, you design contracts to achieve coordination. So you can see that only in step 4 we can do something like this. So you have to do a lot of different things before you reach number 4. In one of the papers that is listed for your presentations is, for example, taking what it is doing is, it's taking a contract structure, formulating the first 3 steps. Actually, the first 3 steps, but it's not possible to get the centralized solution. Okay, in that case, because it's obvious that there is some kind of an information asymmetry. So, I mean, you cannot, it's not meaningful, but what you can do is, under that contract, you can compare what's going on and so on and so forth. So, I mean, you can do a lot of things, but not necessarily offer a certain contractual structure. Okay? But still, I think it will be valuable towards obtaining a contractual structure. Okay. Now, of course, the 4th step and the 2nd step, and even like the third step, the basic tool that we use in OR is game theory. So this is the basic tool which is used. Now, game theory is has been known since 1920s, that there has been a lot of work on game theory. But it turns out that still the gaming background, the game theory background that we require for very realistic supply chain models is not there. In other words, the game theory itself is not sufficient to create this type of structures for reasonably sized problems. For example, the notion of dynamic gaming. In other words, you play a certain game, but you have different periods for which you play this game, is not something that there are a lot of structures known. So, for example, if I'm going to order you, and if the conditions change, not necessarily drastically, but if the conditions change, now if we apply game theory, the current theory assumes that you are going to apply the same notion period after period. Whereas we know in real life that there is something which is called learning. In other words, instead of playing the same game, you start to play the game in rather different ways. A very good example is university entrance exams. When it was first established in the first 5, 6, 7, 10 years, the system worked perfectly because there was no gaming. But after 10 years, everybody learned what was going on. So they started to have different structures like dershanes, okay, which started to exploit the university entrance exams question structure. So what happened at the end is that before they made some changes, the questions started to be more difficult and difficult, but at the same time they lost the way that they are able to measure the capability of a student. They lost that property. So then they made a change to the university entrance exam. Those are the years where they actually changed the exam. So every time that you change that exam, there is like 3, 4, 5 years where it works okay, and then after that people learn. Now if you apply the same idea to dynamic gaming, okay, dynamic gaming is a very difficult concept because there is something which is called learning. If you assume that the game is going to be held in the same way in the consecutive years, it doesn't work that way. So the theory in that respect requires a lot of development before it is applicable to these type of situations, of course. But at least what it does is it gives us a direction with respect to how to think and how to make some agreements, even in the long run. Of course, it gives a direction. Okay. Now, what I will now do is I will probably spend the rest of this hour to talk about game theory. Very little. And my aim is not to teach you game theory, but to give you the basic tools, the basic understanding of how this game theory idea is applied. So this is what I'm after now. And I will try to give a simple example, which is one of the equilibrium, one of the problems that they have in economics. So I will give an example from there. Now, let's say that we have n players. So I will try to explain you the notion of equilibrium. By the way, is there anybody here who took a game theory course?
I took microeconomics.
And you have seen some game theory in it. Okay. And you did. Okay, so you might be familiar with what I'm going to talk about. Now, let's say that we can have different games. We can have competitive games, and we can have non-competitive games. Now, game theory has two main groups of studies. One of them is cooperative game theory, and the other one is non-cooperative game theory. Cooperative game theory means that the players sit down, they think all together, but they want to satisfy certain conditions. So the conditions can be defined in various different ways. There are different concepts there. Non-cooperative game theory, non-cooperative game theory is the branch of game theory where the players do not sit down together. What they would do is they would give their solutions when they are given certain conditions. So as a result of those, there will be an equilibrium reached. They are not actually cooperating with each other. Exactly. Okay, what they are doing is if you give me those set of prices, this is the quantity that I'm going to select. So then I will change the prices that I give. You give another solution. At some point, we will be satisfied and we will stop. Okay? So this is basically, it's non-cooperative. You're not cooperating, but you are playing the game. Okay? Whereas if you have the cooperative game theory, it is different because then you sit down with the partner, okay? And then you decide certain things together. But there, of course, you have to decide some basic minimums. So what are those minimums, and so on and so forth. And that brings different concepts within cooperative game theory. So cooperative game theory is actually mathematically more difficult than non-cooperative game theory. Because then you have to talk about what is fair in this group of people, and so on and so forth, which brings us to very different questions. But both of these theories are applied to supply chains, both cooperative and non-cooperative. The traditional one is non-cooperative. The cooperative one is, I think it's a little bit more modern than the non-cooperative one. Now, certain laws do not allow actually the actors to cooperate. So these are not sort of legal structures, but some of them are also legal structures. Okay? In other words, you cannot collaborate with your competitor. You shouldn't, but there are certain laws against it, but they usually do that. But basically, the theory is different. Now, what I'm going to talk about is non-cooperative game theory. In other words, we have actors which are not going to sit around the table, but they are going to make some bids, and at the end, they are going to be satisfied. That satisfaction point is going to be called the equilibrium point. Okay. So we have n players. Now, I will now talk about the competitive games, and the name of the equilibrium is the Nash Equilibrium. Okay, so how do we approach this problem? Actually, it is very simple to define it this way. Let A sub I, okay, denote player I's best action when the list of other players action is A I minus I. In other words, what this notation means is that we're talking about the actions of the other players, actions of all players except I. So minus I means that you take I out of the set. So we have the actions of the other. So this is a vector actually, and this is not a vector. And in this case, is as bi. So I am going to define bi as the best action that player I can take given the others. So bi is the best action, and it is a function of the actions of the other players, is given as ai is in some set A capital I. In other words, you have a set of actually possible actions that you allow for I. It is in that set. And such that the utility A1, A minus I is always greater than AI for all, and this is true for all for all AI in this set. So the way that I define again is as follows. Now, what you want is you want to select the best action for I given the other actions. Okay? So let's say that we are bidding for something. You give me your bids, individual bids, and then looking at those bids, I am going to select the bid that I am going to make, which is going to maximize the utility that I am going to get from the result. This result is not only a function of my bid, of course, it's also a function of your bids as well. So the utility that I am going to get from this bid, utility can be profit, utility can be satisfaction or anything, any function, and it is going to be the largest possible utility. And the way that I'm going to select my AI is simply going to be this way. So this BI of AI minus, let's say that it's the action which is taken by I, given that this is the set of actions that you already have. So there is nothing actually fancy about this. The only thing that I require is I know what your actions are. Conditioned. So given that these are your actions, I am making my best action to maximize my utility. And this is the so-called BI function. So here in this case, let me give some explanation where U is the utility and B sub I is called the response function. Now, why do we call B sub I as the response function? Is obvious, because if you change your bits, then I will have another response. So for each set of bits that you have, for each condition, I'm going to have a response. So it's called the response function. Now, here, of course, the interesting part is that now each player individually is going to have a response function. Now, I did it for myself, but you can take yourself out and look at the others. So now you see a set of actions which are taken by the others, and then you take an action, and you have a response function as well. So everybody has a response function, given the other A's, the other actions. So what will happen is that if I call the action A star is a Nash equilibrium, if and only if every player's action is a best response to the other player's actions. In other words, A star is such a solution that given the other stars, okay, AI stars, A minus I stars, AI star is the best solution that I can obtain. But similarly, the same thing is true for any other player, for the other J's, K's, and so on, for the other n-1 players. So what is this? What's the meaning of this? The meaning is currently we are in a set where I am given some actions of the other players. I selected my best. But that best, when I give my best and all the other players' actions, except a certain other player's action, the player selects still the same action as I have used. So in that case, nobody wants to change the position, because basically everybody is satisfied. In other words, when do we have everybody satisfied? If I am satisfied, it means that I have selected the best possible action given the other actions. And if everybody is in the same situation, nobody is going to want to move out. Okay? So this is actually the notion of equilibrium. So if I write this clearly, so AI star is in B A minus I star for every player I. Note that this notation allows for possibility of having different actions as a good response to a given set of actions. Okay? In other words, we might have more than one solution, of course. Yeah?
Is this an assumption, the last one?
No, the last one is, this is called a Nash equilibrium if these conditions are satisfied.
Okay, but if we change the A sub minus I.
Star.
Set. No.
But this is also star.
Okay,
Here.
I'm talking about.
Okay, yeah.
If we change the set, then the structure of the BI, does it change too?
Of course. You are going to have another response. But this simply says that if A stars comprise an equilibrium solution, it is a solution where if for anybody, for any player, the best action that you can take, given the other's actions, is AI star. And which means that if this is AI star, then nobody else in this group wants to change it because they are all getting their best possible response. Okay? So nobody is going to change it. I will put this in a little bit different way. So how are we going to compute this equilibrium? Now, if each player, so let me make things a little bit simpler. If each player has a single such response, let's say that each player has a single such response rather than multiple possibilities, and let's call it BI A minus I star, which is equal to actually AI star. Okay, if you think of it. In other words, I have a single response. So you give me your A minus I stars, and I'm always going to select AI star. If that's the case, then we can compute the the Nash equilibrium by solving the following set of equations. So A1 star is equal to B1 A minus 1 star, and A2 star is equal to B2 A minus 2 star, and AN star is equal to BN A minus N star. So you simply solve n equations, n unknowns, and obtain the equilibrium solution. So let us say that my reaction function is a function actually. And how does that function would look like? It will contain A minus i's in it. Okay, your givens, actually, my givens. And then accordingly, I'm going to have my AI. Okay? So it will be a function of the other AIs. So now we have n equations and unknowns where if we can come, sit down and solve this, we'll be able to solve for the Nash equilibrium. Okay. Let me give an example, and then I will discuss a little bit more. This is the known duopoly example. Okay, this is an example where we have two firms. So duopoly means that we have two manufacturing firms in the market, and each firm has a quantity. If Qi is the quantity which is produced, the cost is symmetric, so they have the same technology, as the economists would call it. Okay? So, and where Q sub I is the quantity produced by I. So I is going to go from 1 to 2, of course. And Ci of Qi is the cost of production. So this is actually cost of production. Now, we have, of course, the selling price is dependent on the total supply. So if you have abundant supply, the price may go all the way to 0. If you have a very large supply. If you have very little supply, the price is going to be a large value. So the price is given by, if Q is the total supply in the market, P of Q represents the price, and P of Q is simply alpha minus Q if Q is less than or equal to alpha. It is 0 otherwise. So this is the price structure. As you can see, as we increase the supply in the market, the price goes down. Now, you can always standardize these without any coefficients here and so on and so forth. So it is not a big deal to put A and B here. It doesn't change anything with respect to the structure. Any questions on this? Okay. Now, I am assuming that alpha is greater than C so that there is a value in production. You need to have this condition satisfied. You see, this is the maximum price, is alpha. As the quantity in the market increases, then the price per unit that you can sell goes down. We need to have alpha larger than C so that there is some economics in operation. Otherwise, it's meaningless to do any operation. So this is required for initiating any operation. Okay. Now, let us write the profit function for the first firm. So the profit function of the first firm is not only a function of Q1, but it's also a function of Q2. You can see that. Okay? And, well, what is this? Q1 is the quantity that is manufactured. So minus CQ1 is the production cost that's paid. Okay? Now, note that here there is no uncertainty. Everything is known. Then we're going to receive a revenue, but the revenue is going to be a function of the total supply. So the revenue that we receive is going to be alpha minus Q1 minus Q2, which is the price per unit, times Q1 okay. But of course, we have to make sure that this is positive. If this is not positive, then this is true if alpha minus Q1 minus Q2 is positive. Okay? This is the condition that we need to have. In other words, we still obtain a non-zero price per unit. Now, if we rewrite this, okay, in a more sensible way to reflect this, the price then becomes pi 1 Q1 Q2 if Q1 plus Q2 is less than alpha, then we are going to have Q1 times alpha minus Q1 minus Q2 minus C. Okay? And if this is not the case, if we have an oversupply in the market, then the item that we have manufactured is not going to have any value. So the profit is simply going to be minus C Q1. Okay? So this is basically my profit. Now, let us find the best response given Q2. So now you give me a Q2 value, and I'm going to find the best response. So you give me a Q2 value, and so find best response for 1 given Q2. So you give me a Q2, and I'll find the best response. Now, what happens if Q2 is equal to 0? That's an extreme case. I wanted to take it separately. If Q2 is equal to 0, then what is the best response that I'm going to have? So I will have pi of Q1 0, which is going to be equal to Q1 times alpha minus Q1 minus C. And this is true for Q1 less than or equal to alpha. What kind of a function is this? Over Q1? Q1, nonlinear. It's a quadratic function. Okay? It's a polynomial of degree 2. Okay? And so is it a concave function or a convex function? Now, usually if we have Q1 squared, it would be a convex function, but we have minus Q1 squared, so it's a concave function. Second degree concave function. How many extreme points do we have in this problem? There is only one extreme point. So the function is something like this. It's a quadratic function. So this is when Q1 is equal to 0, okay, the profit is going to be when 0, Okay, so this is Q1 is equal to 0. And when Q1 is another value, the profit is going to be 0. So what is that value? When Q1 is equal to alpha minus C, okay, the profit is still going to be 0. So this is alpha minus C. Okay? In other words, if you overproduce, then it is going to have a result where the profit is expected, the profit is going to be 0. So how can we optimize this? Can you see the optimal solution? So Q1 optimal, you take the derivative of this term with respect to Q1. So this is alpha minus Q1 minus C. And then we have minus what? Then we have the minus 1 times Q1, minus Q1. So Q1 is going to be simply alpha minus C divided by 2. Excuse me, let me write this here. This is the optimizing point. So as you see, as we have a symmetric quadratic function, the optimizing point is sort of in the middle. You have a certain range of production that you can make, and this is in the middle. Now, what can you say about this solution? Q2 is equal to 0. So if the second firm decides not to make any manufacturing, this is the optimal quantity to manufacture. So if I am solving the centralized problem, what will be the solution of the centralized problem? This is going to be the solution of the centralized problem. In other words, if I am sort of centrally manufacturing everything, if two firms belonged to the same firm, this would be the optimal quantity that I would manufacture to optimize my profits. Okay. Now, again, this is Q1 star is equal to, this gives the optimal solution. Now, how about if Q2 is non-zero, well, I'm looking for different possibilities. Now, I accepted Q2 as 0 just to show you that this is actually the centralized solution. Okay? Because we have symmetric technology, so it doesn't matter whether we manufacture it here or there, but this is the optimal quantity to manufacture in order to maximize the profits in the market for the whole supply chain, for the whole system. Okay. Now, what happens if Q2 is positive? Then, of course, the function is still concave, but the limiting conditions are more important. So we are going to have Q1 star simply equal to 1 over 2 times alpha minus C times minus Q2. And this is only true if Q2 is less than or equal to alpha minus C. In other words, if Q2 is alpha minus C or larger, of course, then I'm not going to do any manufacturing. Why? Because then there is nothing remaining in the market. There is nothing that remains in the market. I will never do the manufacturing. Okay. So any questions on this? Now, so it is going to be this 0 otherwise. Now, what we have is, now we have the response function here. This is actually a response function. So now I can write the following. Q1, assuming that everything is going to be in the limits. So Q1 is equal to 1 over 2 alpha minus C minus Q2. And the problem is symmetric for firm 2. Okay, because they are all identical in technology and so on. So Q2 is equal to 1 over 2 alpha minus C minus Q1. So what we have is we have the reaction functions here. how did we find the reaction functions? Given the Q2, I optimized my own objective function, obtained the best possible solution, action for myself, which is a function of Q2. I wrote that equation here. I did the similar thing for firm 2. I have two equations, two unknowns. And you can see that at optimality, Q1 star is equal to Q2 star. Why? Because it is completely symmetric. And then the result is 1 over 3 alpha minus C. So what will happen? So you can assume Nash equilibrium in the following way. I usually, the mathematicians or the game theorists wouldn't like this description that I'm going to make now, because basically they say that the construction is in game theory, in non-cooperative game theory, is such that you create these equations and then solve. Now, the engineering way of describing this is as follows. We are bidding, okay? So you start with a Q quantity, which is, let's say that alpha minus C is 15, okay? So the solution is 5. So you say 6. Then I say, well, when you say 6, then I'm going to say 4.5. You're not happy. Why? Because there is too much production. The supply is still too large, and I'm not making enough profit in the system. So I decrease my 6 to 5, or let's say 550. Okay? And I say 550, and you say 475. Okay? And basically my profit, I can still see that if I decrease my quantity a little bit more, I'm going to make more profit. So I come to 5. The other says 5 as well, and that's the point that you stop, because you know that if you are going to go up or down, you are going to lose profit. So this is the idea of Nash equilibrium. So you can explain Nash equilibrium in terms of a bargaining procedure. Of course, mathematicians are basically very timid with respect to what they are doing. They implicitly immediately say, who is going to start the bargaining? Okay, now that might become an important problem in general if the equilibrium solution is not unique. Okay? Now, let us look at this solution. In this solution, we see that the total amount manufactured is more than what it would be manufactured if there was a single company in the system. This immediately brings us to the following fact that we know. If we have monopolies in the system, usually the supply is smaller. What the competition is going to bring is simply the quantity which is supplied in the system, in the market, is going to be more. This is a fact that we know, and this is usually true. Okay? So this is actually what we see in the simple model, but we also see the application of the reaction functions in a very simple way. Now, of course, there are some technical issues. Now, game theory is not that simple. This is a very simple and nice example. And the technical issues, which are extremely important, because unless you solve those technical issues, there is nothing, it's not meaningful to apply game theory. One of them is, the first one is existence. Now, in this case, we were able to show that a solution, a Nash equilibrium exists. But in general, existence is not a very simple issue. So, but I think there are some very nice results, which are very general results, and that is if the reaction functions are convex, then you always have existence. Okay? Well, I didn't probably. Okay, if the original, excuse me, I made a mistake. If the original profit functions are convex, or excuse me, if the original cost functions in general are convex, profit functions concave, that means, okay, we always have, there is no problem with respect to existence and uniqueness. Okay, but if you don't have this problem, then you will fight with the uniqueness issue, existence issue. Unless you show that it exists, it becomes a pretty ugly problem, actually.
There is several maximum.
Of course, it may not be unique. In that case, what is the meaning of equilibrium? Then the way that I described engineering equilibrium becomes meaningless, of course, because it depends on where you start, if you have local. And it turns out that the economists would usually select the equilibrium points which is Pareto efficient. But those are not the concepts that I want to talk about, but there are some ways of decreasing or obtaining a solution even if you don't have uniqueness. But it turns out that it is very difficult to show the problem structure. For example, I remember we had a problem, again in this contracting business, where we were able to show that it wasn't unique, and there were at most three Nash equilibrium points. Okay? Now, unless you characterize those individual solutions, you cannot go any further. We were able to characterize up to a certain extent. We took the one which yielded actually the smaller numbers. And that we created a logic so that we take that equilibrium as the equilibrium that we wanted to have. But again, as I said, if you don't have these two conditions satisfied, there is no value in what you are doing. And it turns out that this is something, a topic which is pretty difficult. But I think I'm hoping that I was able to give you an idea of how to solve those problems. And next time we have another paper by Eppen and Iyer. We're going to start with that paper, and then I will give some results of contracting. And then we're going to start talking about design, product design, and process design problem in supply chains. That will be the last topic that we deal, and then we're going to have your presentations coming in. Any questions? Okay, I'll see you. Well, this Thursday we don't have. It's our Bayram, Çocuk Bayramı. So we are. I will see you next week. You have a homework that you will submit until tomorrow night, and with respect to your rankings of the papers, I expect an answer from you Monday morning. If by any chance, if you don't give me an answer, then I will make the assignment. Okay? So please rank the papers. Again, if you cannot find the paper, a copy of the paper, please inform me today, latest tomorrow, so that I will be able to mail you. If you inform me on Thursday, I won't be able to mail you because I will be out of city. Oh? Thank you.